So I'm presenting some joint work with Jieying Chen from the University of Oslo on deductive module extraction for expressive description logics. This is based on a paper that was accepted at this year's Jieying. So a quick recap. What is the scope? What are we dealing with? So we are dealing with the problem of module extraction. And the idea is you're given an ontology and you're given a signature containing names, concept and row names, and you want to extract some subset of the ontology around the signature. So in the literature, there's a lot of different notions and properties for modules, and there's a lot of use cases why this is interesting. In this paper, we are focusing on two use cases. One of them is ontology access or ontology understanding. So using module extraction to get some information on a signature. So how are terms in the signature related to each other, or which axioms are relevant to entailments in the signature. And the other use case is ontology reuse. So we want to extract this ontology, we want to extract the module to use it in a new context where we want to avoid the baggage of having to carry too many axioms with us. The notion of modules that we're considering here, we call deductive modules because it's based on deductive inseparability. So we fix the description logic L and the signature sigma of concept and role names. And then we say that a subset M of the ontology O is a deductive module for L and sigma if M and O entail the same axioms that can be expressed in the description logic L using only names from sigma. So with respect to this logic and this signature, we cannot distinguish them. So in the literature, you can find also other notions describing the same thing. So what I found was concept modules, basic modules, and subsumption modules. If you've heard about those, then this is probably what I'm talking about here. And the main difference to other notions of modules is that we focus on what can be expressed in the description logic in question. So if we're interested in other things such as query answering, then this is probably not the right notion. But focusing in this sense has advantages. For example, in contrast to other notions of modules such as semantic modules, we gain decidability here for general ALC ontologies. So in this paper, we consider the description logic ALC and ALCH, and we also consider some additional properties depending on the use case at hand. So the first one is probably at first sight the easiest to motivate. So we're looking at subset minimal modules, because the whole point of extracting a module is to get something smaller. Of course, it would be nice if the module is smaller than as small as possible. The smaller, the better. And an optimal solution will be helpful. But there's also applications, especially in ontology understanding or analysis, where minimality might not be what we want, but we would rather have some sort of completeness in the sense that we include all axioms that contribute to some entailment in sigma. It could be that different axioms contribute to the same thing in different ways. And if we want to supervise these axioms to look for bugs or something, then it would make sense to access all of them. Finally, for the use case of ontology reuse, a very important property is robustness under replacements. And I think this can be best illustrated with a picture. So the use case here is that we want to extract the module to use it in a new context and to extend it to a new ontology. And here, of course, we would like to be able to replace the module with the original ontology without any strange side effects. So they should behave in the same way if we replace the module or the ontology, which should still have the same entailments in our signature. In this talk, I focus on one combination because I think the technique there is quite nice to explain in a short talk, namely the description logic ALC. And for this logic, subset minimal deductive modules that are robust under replacements. So the first observation is an older observation that's been observed quite a while ago by Koopmann and al. And others. In order to be robust under replacements, we need to suffice it to preserve additional entailments, not only entailments that can be expressed in ALC, but also entailments that can be expressed in ALC extended with the universal role. I use this triangle in this work to refer to the universal role. And the second central observation is that uniform interpolation can be used to tell us which are the entailments that we're actually interested in. So here now I have, of course, to introduce a new notion, the notion of a uniform interpolant. And this definition looks quite similar to what we've seen before. The main difference being that we don't require the interpolant to be a subset of our ontology. It can be any set of axioms, but we require it to be fully in the signature sigma. So we are constructing the interpolant using only names from sigma, and we want to preserve all entailments that can be expressed in the description logic L and the signature sigma. And it turns out quite intuitively that this is exactly this covers exactly the kind of axioms we need to preserve by the deductive module. So an example to understand what this is shown below. So on the left we see a small T box with the concept names A and C highlighted, and on the right we would see the corresponding uniform interpolant for A and C with respect to ALC extended with the universal role. And now it turns out for any subset of the ontology O, if this subset entails the uniform interpolant for sigma, then it is actually a robust deductive module. Okay, I could have removed the top row in this case. It's not relevant because that's what gives us the robustness. So, well, this observation motivates a quite simple algorithm. So basically all we have to do is to look for a minimal subset of the ontology that entails the interpolant. So we can, for example, use a sort of binary search where we, what happened? Who's putting these green lines? Okay, there's some green lines appearing on my screen. I don't know why.
Patrick, we don't see anything.
Okay, I don't know what this is. I will just ignore it. Weird. Strange. So yeah, so you just use a standard algorithm. This type of problem has been considered before. It's very close to axiom pinpointing, and in fact, what we're computing here is actually a justification. There's only one problem. If we just use a search like this and we test in each step whether the interpolant is still entailed, then we have to do a lot of entailment tests that turn out to be very expensive in practice. And the reason is that the uniform interpolant is potentially very large and complex, and modern reasoners don't like that very much. And the solution, which might look a bit strange at first, is to compute the interpolant also of the subset and test for entailment between these two interpolants. So we interpolate each subset and check whether they still entail the complete uniform interpolant. And if this is the case, then we know that we still have a module. Why is this more practical? It's because these two interpolants use the same vocabulary, and therefore it happens in practice quite often that they syntactically overlap, and we don't need to perform all the entailment tests using a reasoner, but a lot of it can be done syntactically by simply checking whether the axiom is entailed. Of course, there's now a new problem. Instead of iteratively testing for entailment, we now have to iteratively compute interpolants, and this is actually a more expensive operation. So at first sight, this doesn't look like a good solution. So what we need is some method to quickly compute interpolants for arbitrary subsets of the ontology O. And our approach for this is what we call an annotated interpolant. And this is computed as follows. So for simplicity, we assume the ontology consists only of concept inclusions of this form. And now what we do for each of these axioms, we annotate it by adding a fresh concept name on the left-hand side that uniquely identifies this axiom. And now we compute a uniform interpolant for the signature sigma we're interested in, extended with those labels, with those new concept names L alpha for each axiom in O. And based on the annotated interpolant, we can now compute the UI of any subset syntactically. Namely, if an axiom is included in our subset, we replace the corresponding label by top. If it is not, we replace it by bottom. And we can apply some syntactic simplifications to make reasoning easier. And this way, we were able to implement an algorithm for extracting modules that works also in practice. So we considered some more topics in the paper. So for instance, in order to compute complete modules, it turns out is actually even easier. We can directly read them off from the annotated interpolants. However, what we did not look at is combining completeness with minimality. So it is possible that our method there contains some more axioms that are not necessary for completeness. We also looked at ALC sigma modules that are not robust under replacement. So these could be potentially smaller, but the annotation trick we described before does not work anymore. We have to extend it a little bit. And finally, we extended all methods with role hierarchies. And in this case, the approach of using a uniform interpolation method as a black box does not work anymore. And we have to directly modify the implementation to track usage of these axioms. So we implemented our method for ALCH with the universal roles. And for that, we used an existing tool called Lethe, which we extended to support universal roles and with some bug fixes and optimizations, especially some simplification rules to be able to get nicer interpolants for our method. We used Hermit as a reasoner, and we used a quite different timeout mechanism than usual, in the sense that the step of computing the uniform interpolant was given its own timeout of 5 minutes, while the overall method was given a timeout of 10 minutes. The reason is that if the uniform interpolant method fails within this time window, usually there's only few names left, and we would then continue to compute a module for the extended signature and see whether we still get something small. We focused in this experiment on small signatures with 100 names each, as well as on signatures based on the axioms in the ontology. And we compared our approach with the star modules as they implemented the OWL API, as well as with Amex modules, and we used ontologies from the OWL Reasoner competition 2015. And these are the results. So maybe let me start here. So 91% of cases, the annotated interpolant could be computed within the 5 minutes. In the other cases, on average, there were 2 more names that we were not able to eliminate, and correspondingly, we computed the interpolant for an extended signature, and this was successful in 96% of cases. So this is the complete module that is not necessarily minimal. Computing the minimal module was only successful in 83% of cases, and it turns out that minimizing the module on average took roughly the same time than computing the complete module. So we end up with 44 seconds in total, which is much slower than the other methods, which work more in the range of milliseconds, or at least below seconds. If we compare the sizes, however, we see that our approaches often result in much smaller modules. I'm almost there. I know the time is up. The reason we see here 2 columns is because Amex only supports acyclic ontologies. So we divided our set of ontologies into 2. And with this, I conclude my talk. Thank you very much. And I'm open for questions.